beginning of the summer school. We had really a very nice week, and we are excited to start with new topics. And just a logistic for this week, we will be in this room. And then next week, Wednesday and Thursday, we will be in the bigger room. And if we don't mind, get some conflicts. And that's it. Well, if you need anything, let me know. And let's have a fantastic time. I see you.
Hi, so I'm Guy Blelloch. Actually, on the schedule, it has
put the microphone up.
It has Umut Azar as the first speaker, but we just switched this morning, so we'll be talking after this application. I'm going to be talking about parallelism. We're going to start with the Lambda Calculus. Hopefully, you've all seen something about the Lambda Calculus, and we'll talk about how it's inherently parallel. So the title of this, summer school is Parallelism and Concurrency. Most of this first week is about parallelism. So what I'm going to be talking about is what we call parallelism. And you might, wonder, well, what's the distinction between parallelism and concurrency? Well, parallelism has more to do with actually having what I'm going to be talking about today and mostly for the rest of the week are things which have sequential semantics. In other words, from a semantic point of view, is absolutely no different than a sequential language. And so the parallelism, the only thing it offers you is effectively performance. So it's really, in some sense, an implementation thing. And in order to be able to implement something in parallel, there actually has to be some inherent parallelism in the program. So really the purpose of this is to identify what things can run in parallel, and then run them in parallel without being any different than if you ran them in sequentially, okay? And, so you don't have to think differently at all about how you program. The only thing you have to think differently is about when you analyze your programs, when you try to estimate their costs, do asymptotic analysis, do algorithmic analysis, is how is that different? So what is the new cost? Is quicksort used to be n log n? Running time, now it runs in parallel. What's the right cost model? How do I know how well it's going to run on multiple processes? But it's still the same quicksort. It's still going to sort correctly. If you write a cockproof for it on the sequential version, it'll be valid on the parallel version because they're no different from a semantic point of view. And the way we're going to do that is basically by taking the semantics, and instead of changing them, we're going to add something to them. We're going to add a cost model to the semantics, and that cost model is going to explain to us what the parallelism in the program is. Okay? And beyond the cost model, we're also going to add what we call a bounded implementation, or sometimes a simulation, which says, well, if the cost model gives us some costs, well, are they even meaningful? And the way that we argue that they're meaningful is we show that we can take those costs and map them onto a real machine, or at least into another abstract machine. Because as I'm going to explain, none of the machine models are actually real machines. So it's basically augmenting the semantics with something that gives you an idea of costs. And if you were here last week, I believe there was some discussion of cost models, so you've probably seen this before. And here we're doing it in particular in the context of parallelism. So that's going to be the topic. Now, a lot of what we're going to be covering, at least what Umut and I are going to be covering, are stuff that we actually teach at CMU in a course where we basically take the algorithms course, and this is the algorithm course that all of our students take, so all of our undergraduates take it, and it's taught completely in a functional style. So they learn algorithms from a complete functional style, and everything we're going to be doing here is pure functional, no side effects, at least at the user level. Now, under the hood, we'll talk about implementations, and in the implementations, there'll certainly be side effects and low-level details. But from the point of view, the semantics is purely functional. So we teach this algorithms course in a purely functional style, and furthermore, it's all parallel. The course is, we teach parallelism from the beginning for the end. And the way that we teach parallelism is in a way that it's not unfriendly to sequential algorithms. So in some sense, as we'll see, the sequential algorithms fall out as a special case of the parallel algorithms. So we teach quicksort, and if all you cared about is how long it took on one processor, you would still learn exactly the same you would have in your standard sequential algorithms course. But you'll also learn how well quicksort runs on a parallel processor as an addition. So that's the basic idea, and what we get is basically you can do all the standard algorithmic results in a model that's purely functional, and get them parallel versions of them as well. And so that's largely a topic we're going to be covering, at least Umut and I. There's of course there's other lectures as well that Umut and I will be covering this week. Okay, so what I'm going to start with, and by the way, mostly we're going to be talking on the board, but this first talk I'm going to give with slides. And then I think from the rest will be on the board. So I'm going to start with talking about the Lambda Calculus as a cost model. So we're going to look at the semantics of the Lambda Calculus and augment it with a cost model, talk about simulations, and look how that all goes. We're going to compare it to other sorts of cost models. So you've probably all taken an algorithms course, learned about the RAM model. You got some unbounded memory, some processor, you assume constant time access for reads and writes. Some of you might have seen some parallel models like the parallel random access. So we'll talk about how this relates to those models. Okay. So here's the Church-Turing Hypothesis, pictorially. That's a lambda term. Oops. That's a lambda term at the top here, right? Beta reduction. So lambda calculus is basically beta reduction, right? And then we have a Turing machine at the bottom. It's got some tape and some state. This seems to be a mechanical version of it. And of course, Church-Turing argued that they're equivalent, right? The Church-Turing hypothesis. And not only that they're equivalent, but probably any reasonable computational model you're going to come up with are equivalent in the sense that they compute the same things, right? And the same set of functions can be computed by these. And since then, there's been two quite different communities that have gone off. There's a programming language community that's focused on the top there. There's sort of Lambda Calculus and extensions to it. And there's been the original Lambda Calculus was untyped. In fact, I'll be talking about the untyped version today. And then, of course, there's been all sorts of types added to it, all sorts of extensions. And then, of course, the complexity theory, they sort of started the Turing machine, and they went to the RAM and a bunch of different machine models, and they sort of diverged. And part of what I want to argue is that maybe they should merge back together, that maybe we shouldn't have this one community, the complexity theory, working on machine models, and another community, the programming theory community, working on Lambda Calculus type models. And so we'll see how these relate. By the way, anyone should feel free to ask me a question at any point. Don't feel to keep quiet. So let me just start out by a little history here on, again, the goal here is, yes, it's true that these two are equivalent in terms of what they can compute, but really there doesn't say much about the cost. Like, if I compute something in the Lambda Calculus, how does it relate in cost to what I compute in the Turing machine? Now, the cost in a Turing machine is often very well defined because it's just a number of steps. The Lambda Calculus is a little more difficult to get your hands around what it means because, first of all, there's lots of different reduction orders we can apply in the Lambda Calculus. We can choose, there could be lots of different reduxes within a Lambda term, and we can decide which one we're going to reduce, and that makes a big difference. Today I'm actually going to be talking about just one reduction order, which is the call by value reduction order, where we, if we're applying one expression to another, we first fully evaluate both expressions, and then we plug in the second one into the, assuming the first one evaluates to a lambda, the second one into the first one. Okay, so machine models and simulation. There's something called the Handbook of Theoretical Computer Science. This is a big tome. It was originally published in 19
90, and it's full of, it's got an article by Bob Tarjan, one by Knuth, it's got, all the famous theoretical computer scientists. The very first chapter in that handbook, and by the way, by theoretical computer science here, they mean the complexity side of theory. So there's absolutely nothing about the Lambda Calculus in this particular book, right? And the first chapter is on models, because you sort of have to start with a model. So it talks about, well, all the different models of computation, and it's titled Machine Models and Simulations by Peter Van and Bose. And then if you read the very first page, okay, the first paragraph is some fluff about the chapter as a whole. The second one is basically saying, well, if you want to understand complexity, analyze algorithms, understand the relationship between them, ask questions about P versus MP, anything that involves resource bounds, then you need some measure of complexity in your model. You need some measure of time, space, and there are other things you could possibly measure. Maybe you could measure energy, etc. And so you need some way to do that. So you need some formal model for this purpose, right? And then it goes on, it says the conventional ways to model this is by the notion of abstract machines, okay? And it's important to point out these are abstract machines. Is that Van M. de Bose didn't, even at the time they realized the machines they're talking about, the RAM, for example, the random access machine, is not a physical machine. You cannot build a random access machine directly. As in reality, you've got caches, and if you want to go get a memory, it has to go up through multiple switches, and so it's an abstraction. It's nothing that's physical. Okay, and that's important because once you say it's an abstraction, then you say, well, why do my abstractions have to be limited to machines? Okay, because it's a virtual machine that we're basically saying, well, we're going to map it down onto a real machine by building switches and networks and all sorts of things that go under the hood. But we've abstracted it into this abstract RAM, is for example. And then he says these are called machine models. So there's an inherent bias here that basically says it has to be a machine model in order to be a cost model. And basically what this first talk today is about, well, no, they can be language-based cost models. And since they're abstract, there's no reason they have to be a machine model, right? Because it's a virtual model that you're basically building one on top of the other. Now, what is important, on the other hand, is this notion of being able to simulate one model in terms of another. And this is true even if we're just talking about machine models. In fact, the third paragraph in this chapter that was after the one I just showed you is the following, that says, well, there's lots of different abstract models. We have RAMs. In fact, there's 7 different types of RAMs. We have different sorts of Turing machines. There are pointer machines. There are all sorts of different machines. And the argument is, well, it doesn't matter that much which one you use, as long as you know the relationships between them. So it's very important that you can then write down that if it runs at this time on this machine, if I translate it to the other machine, I don't know, square the time, divide it by 26, and multiply it by 5. Now, normally we don't care about constants, but and why would I divide by 26, multiply by 5? But anyway, the idea is that you have these mutual simulations. And in fact, if you look at this chapter, I would say 1/3 of it is on the actual models, defining what the model is. The other 2/3 is on simulation. How does it take to simulate? And even if you look at a RAM, there's several different versions. And so they'll say, well, if we have a RAM with addition and we want to simulate one with multiplication, here's the slowdown we get. If you have a RAM, it turns out if you have a RAM with unbounded word size and multiplication, then you can prove P equals NP. Okay, and that's actually where the simulation is important, because then you say, if I try to simulate that RAM, where I have multiplication and unbounded register length, you'll find out I cannot possibly simulate that efficiently on a RAM which either has bounded registers or takes away multiplication. And that will tell you something. It'll say, well, maybe that model's too powerful. And indeed it is. Okay, and in fact, the best anyone knows how to do, unless p happens to equal np, is it will take exponential time to do that simulation. To simulate just a random access machine where you don't bound the length of the registers and you have multiplication, you can basically do anything you want with it. Okay. Does someone know why such a machine is so powerful? If you had unbounded register length, or each memory cell could have an unbounded number of bits. Why p equals np in that model?
It's unbounded, so it can just do anything.
Yeah, the answer is parallelism. Okay, and it's unbounded, so what you can do is you can simulate parallelism in a word, and instead of doing one operation in a word by various tricks, you could do a million adds, or billion add, or an exponential number of operations within that word. And so you could simulate unbounded parallelism, and then you could do a exponential amount of work on every single step. Okay. So the point here is that it's important to have these simulation results because they tell you that your model is bogus. They tell you, oh, you're assuming you can do this crazy thing, and if you assume that p equals np, and if you analyze your algorithms in your model, you'll soon find that exponential time algorithms seem to run in linear time or something. So the point is there's sort of two parts to a computational model. There's the model itself, and then there's some way to verify that it's a reasonable model. And the way that that's done typically is by comparing it to another model. And you can compare it to an even lower level model. So I could take a RAM and I say, let's say I only have circuits with bounded fan in and bounded fan out, which are much more realistic. So you're actually going to build it in a physical hardware. You can't have, unbounded fan in and fan out, which effectively the RAM assumes. So you say, I'm going to build it with one, and you get sort of like a logarithmic overhead for the switches, and you can say, I can simulate the RAM on a machine with bounded fan in and bounded fan out with log extra cost or something. Yes, in the back?
I just want to make sure you're not saying you start with a Turing machine with
With
you can simulate parallelism. Is that what you're saying?
the simulation result, you're saying?
Yeah, you're saying just the assumption of an infinite table. Then
Not if. No, the assumption is I have a. So the one where p equals np is, let's say I have registers which have an unbounded number of bits, like a RAM register. Okay, and I'm allowed to multiply two such registers in unit time. Because in the RAM model, you assume all arithmetic operations are constant time, unit time. And if you assume, then you're in trouble. Now, if you look at in the fine print, if you look at a correctly written theoretical paper, it'll say, no, you can't have an infinite number of bits, you have a logarithmic number of bits. So it's very important in the RAM model, whether you were taught this when you did your undergraduate algorithms or not, it's extremely important that you limit the number of bits in each of those registers. Okay? Otherwise, you can do crazy things. So if you then go on and read the chapter, it talks about, there's 50 pages of machine models and simulations. It talks about all sorts of different Turing machines. It talks about all sorts of relationships between them. How long does it take to simulate a two-tape machine on a one-tape machine, or a stack machine on a tape machine? And there's all these kind of tedious, boring results about simulations of Turing machines. And then there's also many different versions of random access machines. Okay, and I've mentioned these. You can have the SRAM only have successor and predecessor, doesn't even have addition. The RAM has add and sub, and the MRAM has multiply. And then it's got various restriction on the length of the words, which I was just discussing. So you could assume that the word lengths are basically, and you could ask also, well, what does it mean logarithmic in n? What is n, right? Because in RAM has you assume an unbounded memory, so n would be an infinity. Okay, so you have to ask, well, what is n? N is normally the input size. So you assume whatever your input size is, the number of bits in your register is log of that input size. And you have to assume this. You might not have been told this in your intro to algorithms course. And Then there's ones where you actually pay based on the word length. So if you do an add on 2 registers, you actually pay based on the number of bits in those registers. And this one's, it's actually a reasonable model in the sense you can simulate these. Okay. Mm-hmm. Well, you need, so yeah, why log of n? The answer, yeah?
Can you repeat the question, please?
Oh, the question is, why log of n for a register length? It turns out you need log of n because you need to address any memory location. So you want to be, in the RAM, you want to be able to have an address. So you need it to be at least log of n so that you can address anything. And so then why don't you assume it's log of n? So that's one answer, that's sort of a minimum you need to make the RAM reasonable, just to be able to express an address in a register. The second part of that question is, if you look in practice, machines, as they've been growing over the years, the register size have all been growing as basically log of n. So at one point we had 8-bit registers and 16-bit, and they could only some tiny memory, then 16-bit registers, and we could have 64,000 memory locations. Then there were 32 bits, and now 64, and they've scaled effectively as a log of the size of the machines. So practice has matched that theory. There's also all sorts of simulation results between the different RAMs, and most of them are, anyway, so you can write these down. Okay, there's also a bunch of parallel machine models out there. So there's machine models. Now all the models I talked, the Turing machine and the RAM, of course, sequential models. There's some parallel ones, and there's dozens of different ones, and this chapter described some, and in fact there's been more since this chapter was written. There's the circuit models, where you analyze things in terms of the number of gates in a circuit and the depth of a circuit. There's vector models. There's a parallel random access machine, and in fact we'll talk a little bit about simulations today. So we'll basically introduce the Lambda Calculus as a parallel model, and then talk about how we can simulate in a PRAM. And a PRAM is basically just a parallel version of the RAM, so you have some memory M, and instead of having one processor, you have some P processors here. Okay, so and that P is a parameter of the model, and each of these processors can access the memory in constant time, the assumption. And we'll have the same restriction that the registers in this memory locations have logarithmic number of bits on the input side. And the point is, all these processes can take steps together. It's typically assumed that they run in lockstep. So they all do an operation, and then we count the number of steps which are taken. And now each step, instead of doing one operation, can do P different operations, as long as we've got P things to do. So anyway, and then there's all sorts of simulations between these models. So the bottom line is that what we have is a lot of models. Furthermore, these are all virtual models. Right? In the sense, the PRAM, you can't possibly build a machine where you can, in unit time, access a memory. Again, there's switches in here. It has to go through some network. It has to communicate. So it's an abstraction. It's not something you can build. And all the machines on here, even the circuit models, you could say, well, maybe I can build a circuit. But there's various unrealistic things about these circuit models. In particular, you assume you can generate a circuit of an arbitrary size instantaneously. Right? I actually have to build that circuit. So they're all basically abstract models. And so coming back, we say, if we're going to make an abstract model, why not make it a programming-based? So anyway, there's two parts to a typical model. Any of these cost models I mentioned. One is the model itself, and it has to have a well-defined semantics, just to make sense of it, or even to be able to formally specify the costs in the model. Typically, you want it to be simple. Otherwise, it's very hard to deal with. And ideally, you'd like these models to be close to the programming paradigm. And I claim that in the sequential world, the RAM has satisfied this property, the random access machine, because C is basically assembly code for the RAM. Right? So if you, most algorithms courses are taught in either C or pseudo-C. Okay? A pseudocode that looks like, that basically is the same as C. And so it's effectively assembly code for this RAM. And so when you analyze your code, it's easy to map it in your head to cost in the RAM. This is no longer true in the parallel world. And that's why it's now important to rethink this. Okay, and then the second part, once we have a cost model, is the simulation. We want to be able to say, oh, I've got this model, and ideally the model doesn't show us P equals NP. It's probably broken. So we'd like to be able that we can simulate this efficiently in some other model, maybe a more realistic model, maybe an actual something that could be built as a machine, and know that that goes pretty well. So then the question is, coming back to the Lambda Calculus and the Turing machine, all that previous work had been done in the sort of machine type models. And what we'll be looking about is, can we do this in a language-based model? And so in a language-based model, so in those other machine models, it's based on the number of steps the machine takes, or in the case of a circuit model, it's the number of circuit elements and the number of wires in it and the depth of it. Here, it's going to be based on some cost semantics. I think he talked some about cost semantics last week. We're going to talk about the Lambda Calculus. And why the Lambda Calculus? Well, it's simple. It's clean, and we'll see it can go an awful long way. Now, we're going to extend it in a couple ways. We're going to extend it to have some constants built in, like integers, so we don't have to encode integers using messy ways. And we're going to extend it with arrays at some point, but there's going to be simple extensions to the Lambda Calculus. And then we're going to look at what the cost is. And one way to analyze cost is you might say it's the terms of number of reductions, but that by itself turns out to not be very helpful. So we're going to do something slightly more advanced than that. Okay, and so, well, why do we want to define a cost model on the language? Well, I'd say it's particularly important when we go to parallelism, is it turns out the Lambda Calculus is inherently parallel. So in 1929, when Church first invented the Lambda Calculus, he invented a parallel model. Okay, I don't think he thought about it that way, because when he discussed beta reduction, he sort of talked about it doing beta reduction at one at a time, but it was an inherently parallel model, okay, as we'll see. And the Turing machine is absolutely not. There's no way to do parallelism. So Church had the insight to know that parallel machines were coming along at some time in the future. So it's more elegant, and maybe that's taste. Okay, so I'll say it's more elegant. Maybe if I was in a complexity crowd, they'll say, well, the Turing machine's more elegant. But the other thing is it's much close, especially when you get to parallelism. This model that we're going to discuss is much closer to what I actually, for me to look, I can look at a piece of code, I can map it to this model, as we'll see, very easily. It's a real mess to try to map algorithms to, for example, the PRAM model. It's sort of a nightmare. So it closely matches the code. And it's also, we'll see that in terms of the simulation, that these cost models, we can simulate it. And in particular, what we can do is we can simulate them on a PRAM. And we'll go there. Okay, there's been, the disadvantage is if you go look at complexity, like I say, that whole chapter doesn't mention programming-based cost models once. And in fact, that whole book doesn't mention the Lambda Calculus once. There's a whole book on the theory of computer science without the word Lambda Calculus showing in it. Well, actually, maybe it shows up once in passing or something. Okay, there's been some work on this. What I'm going to be focusing on here is basically the call by value Lambda Calculus and its extension with arrays. So that's what we're going to be defining today. Turns out that you can make cost models for call by need, Lambda Calculus, and you can make cost models for various other things. You can even make cost models that account for cache locality in a language-based model. That seems a little tricky because the cache seems like a very hardware-based thing, but it turns out that you can do that. In fact, that's work where Bob Harper and I did a few years ago. Okay, so let's stick with the call by value lambda calculus. That's what we're going to be talking about. So we should all know what the lambda calculus is. You have expressions which are defined recursively. They're either variables or function application where we take E1 to a lambda and E2, and then we base, and E2 is the argument, and we basically plug in the result of E2 into E1, and then we have lambdas themselves. That's a whole thing. So it's certainly a very simple model. And then we have various rules for evaluation. And these are the call by value rules, okay? Yeah, lambda calculus allows different beta, we can have different beta reduction orders. This is the one where we fully evaluate, if we have E1 and E2, we fully evaluate E2 before we plug it in. We fully evaluate both of them, and then we plug in the value E2 into E1. And that's why it's called call by value, because we always evaluate it out. If you have a lazy language or call by need language, then you could plug in E2 into a lambda here before E2 was even evaluated. And lambda calculus in general allows that, but we're going to be using just call by value. And so if you have call by value, these are basically the rules for evaluation, right? A lambda evaluates to itself, and it turns out we don't even need a rule of what a variable evaluates to. Can someone tell me why we don't need a rule for what a variable evaluates? Because by substitution, but I will never get, well, if it's a correct program, if I don't have any free variables, I'm assuming my original lambda expression doesn't have any free variables, I'm always going to substitute in, and I'm never going to see a variable at the least. Okay, so to evaluate E1 and E2, I, of course, evaluate E1. It turns out to be a lambda. I evaluate E2. It's a value. In this case, values are only lambdas themselves. I'm going to extend it to have more values in the future, such as integers, etc. But at this point, the values are themselves lambda. And then I just do a substitution, and that gives me a v prime, and that's what this is. And that's a whole rule. I just apply this recursively, so I now apply this rule to E1, I apply it to E2, and any program has evaluated this. So this is the whole lambda calculus, right, with rules. Any questions about this? Or? So I assume you saw some of this note. Oh, you've either seen it before or last week. You've seen these sorts of rules for notation, right? Okay. Okay, the lambda calculus is parallel. Particularly the call by value lambda calculus is parallel. Because you've got that E1 and the E2, and I can run them in parallel. They don't interact with each other. So in fact, I can run them in any order. I can either evaluate E1 first or E2 first, or I can do them at the same time. Yeah?
A call by name isn't parallel.
Call by name is not parallel, that's correct. And the reason call by name is not parallel is because I'm not allowed to evaluate E2. I actually have to pass it in immediately. So I cannot do the two of them in parallel. So call by name is inherently sequential. Laziness is inherently sequential, and whenever you see people talk about parallel lazy languages, the first thing they say is strictify it. So the first thing they say is convert it to call by value. And that's the only way you can get parallelism out of lazy languages. Okay, but call by value is parallel because I'm allowed to fully evaluate V2, basically E2 in parallel with E1. Now, of course, you probably know that call by value and call by need have different termination rules. Okay, so there could be programs that don't terminate in call by value that terminate in call by need. Okay. So that's the semantics of call by value lambda calculus. Well, what's the cost model? And then the other part of it, how does it compare to maybe more standard machine-based cost models? And that we're going to look. So it turns out that the cost model we're going to use for the rest of this week is actually a very simple one. Is we're going to add two costs. We're going to add work and span. Okay, so work is going to be, in some sense, a sequential work. And in fact, as I mentioned at the beginning, sequential algorithms sort of fall out as a side effect of the way that we do these. If you just ignore the span and look at the work, that'll be your sequential. So quicksort, n log n work. Merge sort, n log n work. Insertion sort, n squared work. You know, breadth first search, linear work, and the number of edges. Okay, so it just that's the work. It's in some sense the sequential time. It's the number of operations we do. So if we're going to evaluate two things in parallel, we just add up the number of operations in one with the operations the other. It's a total work we do. And that's why we call it work. We don't call it time because it's not time, because we're going to run this in parallel, and the time ideally is better than the work. Now the span is the depth of the computation. Okay, I'm going to be using the letter D for span because well, S sometimes gets confused with space. So, and D, but the reason I call it D is that we also sometimes call it depth. And if I ever use the term depth, interchange it with span. Okay, it's sort of like if I look at the dependencies in my computation, it's the depth of dependencies. It turns out to be closely related. I mentioned the circuit models where you look at the total number of elements in the circuit and then you look at the depth of the circuit. It's related to the depth of a circuit. It's like we can do a bunch of things in parallel by looking for the longest chain of dependencies. And that's sort of going to tell me how much parallelism my computation has. Okay, well, how do I take my inference rules here? There's only two of them, the lambda and the app. And the lambda is trivial because it just returns itself. And add these costs. So I want to make a cost model. And so what I can do is I can just add them. So now the relation, instead of a expression returning a value, and in this case, like I say, values are lambdas, I actually return three things. So I have rules of this flavor, which say take an expression, return a value, the work, and the span, or the depth. So what this rule says is, if I'm going to analyze the semantics here, is it's going to say I'm going to evaluate this expression. It's going to return some value with some work and some depth. And that's the definition of my cost model, is the work and depth. So if I apply my rules on a particular expression, it's going to calculate its way through, go through, and it's going to return a value, which is what it would have done without the cost model, and a work and a depth. Okay, so that's what it looks like. So we have the lambda returns itself. It takes unit work, unit depth. I mean, it just returns itself. It's not zero because I actually have to somehow return myself. So it does have a little bit of cost there. Now, what you do is, I only had one other rule. And what this other rule says is I'm applying, basically I'm now going to evaluate E1 and E2. I'm going to evaluate them in parallel. It's called by value, so I'm allowed to fully evaluate E2 before plugging it in. And so I evaluate them in parallel. They each return a value, which I call, well, I guess one of them has to return a lambda, the first one. And they each return I guess in this case, they're both lambdas, along with the work. So it took me some amount of work to evaluate E1, some amount to evaluate E2, and some amount of depth or span to do E1, and some amount of span to do E2. And the total work is just going to be the sum of all the parts. Oh, and then I have to do the substitution. So then I substitute in the value for x, and then I evaluate that, and it gives me a third work and a third span. I just add up all the work. There's three components, and I add up the work for them, and I add one more in for good measure. Okay, the one more, I have to fork off these things. I have to do some manipulation. By the way, the constants don't matter here. Remember, the purpose of this model is asymptotic analysis. In reality, it's probably going to be more than one. It's going to be some other bigger constant, 4 or 5 or something. You have to, do some steps. Now you look at the depth is, of course, the more interesting one. Is instead of just being the sum, it's the max of D1 and D2 and plus D3. Can someone tell me why it's plus D3? That's right. It has to do, so I have to basically, I'm going to run both E1 and E2 in parallel, but they both have to finish before I can plug it in. Now, yeah?
So we are assuming that E1 can run in parallel, but what about inside E1 I have instruction which can run in parallel?
They will recursively. What happens, let's say E1 and E2 will run in parallel. So let me, so what happens is, right, so I'm going to fork off two things, and E1 is going to run in parallel with E2. Now E1 itself could be another pair of expressions, so it could fork off two more. And it could fork off more. So there's an unbounded amount of parallelism that you could do just by the fact that you're recursively running these things in parallel.
So, but we are having W1 for E, right? So how we are capturing this recursive cost for that expression?
What do you mean W1? Well, what happens, I just inductively, I say E1 is some expression. I'm going to calculate the work for this and the span for this, as well as the value. And, now it's just a level of, I forget that I ever did this. I'm now just going to value. And then if this itself could be another expression, okay? Or it could be, something that then, a recursive routine written thing. So this could be any cost here. Yeah? It's the E in the lambda. So if you look at E1 evaluates the lambda x dot E, it's the dot E here.
Okay.
So I take basically the body of the lambda, and I plug in for the body of the lambda, every place x appears, the value. And then I evaluate that. So that's just substitution. Any other? Mm-hmm.
So in the first rule, could the cost be ever zero? Like we just assume it has to be 1.
Could it be what?
The cost W here, we have called it 1 for
Yeah.
lambdas.
Could it be 0, as you ask? I like to put a 1 there, but technically you actually could put a 0 there, because as long as you have a 1 in front of the max and the sum there, you can show that it's only going to differ, because it's going to be some tree, and the number of internal nodes of a tree is always with as large as the number of leaves of the tree, and so it's only going to make a factor of 2 difference if that's 0, 1. So it won't make that much difference, but I like conceptually to think that it actually takes a little bit of work to return that lambda. Any other questions? You can also view this as sort of like a DAG of dependencies. You can say that I'm going to evaluate E1 in parallel with E2. That's what these two things. So if you look at the dependencies, it starts at the top. So it says I have to wait for both those to finish, and so that's why it's going to be the max. And then when they both finish, then I can do the substitution, and then I could evaluate the substituted body. So I substitute into the body of the lambda. E is the body of the lambda. I substitute my calculated V for x, and I then get V prime. Yeah?
Why would you need the first complement sequential part? I think why just not keep the span?
Why not just keep why do we keep the work in addition to span? Okay, the motivation with that, in fact, will be the second lecture today that Umut will give. So there's a scheduling. I'll give you some bounds. When we map this onto more realistic machines with a fixed number of processors, it turns out the work matters. That it matters a lot, that we actually care about the work. In fact, what we tell our students in this course we teach is actually the work matters more than the span. Okay, that the first goal when designing an algorithm is you want to make it work efficient. What it means to be work efficient is that work is the same as a sequential running time. So if you're going to be designing a sort, you want that work to be n log n. Okay, and then you want the span to be as low as possible given the work is n log n. And that will tell you how much parallelism there is. And that comes out in the provable implementation bounds that I'll mention them, and then Umut will talk more about how they actually come out. I don't know why that came in reverse order. So, of course, this Lambda Calculus is an awful simple language. But you've probably been told that all other sorts of things like lets and data types, pairs and tuples and sum types and product types, case statements can all be implemented using the Lambda Calculus, well, it turns out you can make a stronger statement. They can all be implemented with constant overhead. So I can write an if statement where I only have to pay constant for doing the if statement. So if I evaluate, I have if E1, right? So if I have a statement that's if, E1, then E2, else E3, or maybe I have a case statement which has similar sort of structure. Well, what would I have to pay? I have to evaluate E1, so the work will be E1, and then depending on whether this is true or false, I'd either do the work of E2 and E3. And there's no parallelism here because I have to evaluate one before, so the span will also be the sum of either the span of E1 and E2 or the span of E1 and E3, depending on the value of E1. But that, I don't have to build that in. That if that just comes to me, if I just use standard encodings of conditionals. In fact, they look like this. So they're not even complicated, right? So this is how I encode in Lambda a pair. That's how I do first, and that's how I do second. Local binding is trivial. It's just a Lambda E1, right, a let. Conditionals are also quite simple. Recursion, the Y Combinator will do the job. Constant overhead, okay? Now, since we're working in call by value, we need you might know there's a call by value Y Combinator and a call by need Y Combinator, and they're different, okay? But it's just, Y Combinators, I can write it down in Lambda expressions. It's not much more complicated than, for example, the if then else rule there. So I can write these all down. They all give me constant overhead. So the amount of overhead I get here by instead of building it into my language, simulating it using this is some constant for each of the operations. Now, integers I cannot simulate them in constant overhead, but it turns out I can simulate them in logarithmic overhead. So if I have an integer of size n and I want to add two integers of size n, in this model, I can add them in log n work. Okay, it turns out I can add them in log n span, but it doesn't matter. So there actually is parallelism in the addition, because I can add the bits together, and then I have to do the carry propagate. That's a little more complicated, but I can do it in log n work. Okay. Later, we're going to mention that, well, maybe what we can do is we can just add integers as built-in constants, and then we don't even have to pay for this logarithmic cost for simulating integers. Okay. Does everyone believe this, or want some justification? Yeah?
Tuples up here, so n tuples constant in the length of the tuple, I guess.
Yeah, I'm assuming constant length tuples. We will later talk about arrays, which are non-constant length, where you can build an array of arbitrary length. And then we have to build it in. We either build it in or you're going to pay a log n overhead in the length of the array to simulate it. Okay, so I guess I'm almost running out of time. I went too slow. What? Oh, 25 minutes, okay. So you could say we have this cost model, and you say, well, how is it a reasonable cost model? So if we go back to the original discussion about the chapter by Van Amdebose, he says, well, you basically want to show simulations. So we're going to do the same here. Is we can say, if I've got this cost model, can I write down a proof that says some cost in this model map to some cost in some better known model? And one obvious one is, well, how do these costs relate to costs in the RAM? Let's say I only cared about sequential costs, and how do they relate to cost in like the parallel RAM? How do they relate to cost in circuit models? How do I do these cost simulations? And it turns out it's not that hard. So that's the second part, because we can make up some model where the costs are 0 for everything and say, oh, look, my algorithm is exponential time in the RAM, but look at my model, it's 0. So mine's a better model than yours, right? You don't want that, right? You want to be able to say, in fact, it's the opposite. You want to say, if it's exponential cost in the RAM, it better be exponential cost in your model. Otherwise, there's probably something wrong with your model. Okay, so you might say, I'm not going to go in much detail, but if we, for example, wanted to simulate the call by value lambda calculus, let's forget for parallel for now, just sequentially, could we show that the work, if we're doing sequentially, we don't even care about the span, can we show that we can simulate any expression in linear in the work? So if that lambda, if I basically put an expression in and I evaluate it using my rules, it's going to give me a work. And I'd like a theorem that says that if I can simulate this on a RAM in that much time, then it would be an efficient simulation. It says that this is a meaningful work. It's telling me it actually exactly matches the RAM. Well, it turns out that's almost exactly true, is I can basically simulate the lambda calculus on a RAM in time that's proportional to the work. Okay? And you can do this by, there's different ways you could do this. One way is to use a CEK machine, which is basically a transition machine for evaluating the lambda calculus. You have some control, some environment, some continuation. The control is basically different sorts of expressions, right? Either a function application or lambda or just a variable. The environment is a mapping from variables to their values. So what happens is I'm going to keep an environment. I'm not going to use substitution. It turns out substitution is not efficient. Okay, if you want to, the semantics of the lambda calculus is most cleanly stated in terms of substitution. The implementation, you don't want to do substitution. It's a horrible thing to do. Because you have to go trace down all the locations of your variables. You have to do substitution. You might have many copies of those variables. It could be very expensive. So instead, we have an environment that says, when I basically have a lambda, instead of doing a substitution, I say, well, I know that this x should be bound to v. I just keep track of that. I keep a mapping from x to the value that it's bound to. This is how real programming languages are implemented anyway. You have some environment. So, and then you have a continuation, and you can think of that as sort of the stack, right? Is you basically, and then you can basically build by some simple rules. And there's not many of them to simulate the semantics. Is right. I remember I mentioned there's basically three possibilities for my, what was the first one called? Is it control? By the way, continuation is a K because we can't have two C's. It can be the C, C. So, you know, we can either have the control can either be a function application, it can be a variable, or, and remember in our case, values are only lambdas. So it could be lambdas. And these are just simply the rules, that if I'm applying E1 to E2, I first evaluate E1 with the same environment, and I push onto the stack the fact that I'm then going to have to evaluate E2 at some later point. Then when I'm done, right, if I've evaluated a variable, I just look it up in my environment. I have this environment, it's a mapping to variables to the values, I just look it up. That's it. If I evaluate a value, well, I'm sort of at a base case now. If it's a value, I can't do anything more with it, so I have to pop the stack. Right? So what I do to pop the stack, well, there's two possibilities. The stack either has arg or fun. Well, there's actually a third possibility that the stack is empty, in which case I'm done with the computation. So if I had a V, an E, and an empty stack, that's the termination condition. Otherwise, I pop the stack, and if there's an argument on there, then I go evaluate the other one. So I first evaluated E1, then I come back and later evaluate E2. If I've now evaluated E1 and E2, which is the case that fun is on there, then I do the substitution, except I don't really do the substitution. I now just extend my environment with a mapping from X to V. Right? So remember, I've just evaluated a lambda x dot e. And so what I'm now going to do, I'm going to start evaluating this. Instead of substituting x into here, this is in the context of some environment. Instead of substituting x in here, I'm going to just keep e as it was, but I'm going to extend my environment with saying that x's value is, you know, let's say I applied this to v, x's value is v. Okay, and that's the whole simulation. And this is and then you can think about how would you implement this. And like if you took, this would be like a freshman level, sophomore level implementation of how to do this. Everything's constant time here. Okay, well, that's not quite true. It's a white lie. Everything's almost constant time because, I look like in the first one, all I'm doing is moving things around, right? It's pretty much I'm taking an E2 and moving it somewhere else and taking the E, copying the E and the K, some trivial amount. Can someone tell me the only things which might not be constant time? What? The lookup and one other thing. Insertion, yeah. And it depends on how I implement the lookup and insertion. I could make the insertion just a linked list, in which case I could make one of them, the insertion constant time if I wanted to. But this is just a dictionary. Like these are just variable names. So how expensive if I used, if you go back to your algorithms course and you did a dictionary implementation, it turns out that hash tables cannot work here because it has to be a persistent dictionary. I have to, because I actually keep the old value v when I make the change. So I cannot use a hash table here. But I can use a tree. I can use a tree, and so it would actually be log in the size of the environment. So you can simulate every step here and log in the size of the environment. And the environment size is the most number of distinct variables in your program. Most programs only have a constant number of distinct. Even if you're encoding very big data, you can easily do it. Like if you encode a linked list using, I showed you various encoding schemes. The scheme here, there'd only be a constant number of variable names. So basically, constant in the number of logarithmic in the number of variable names, I can do it. So that's the story. So what it says is every single step I can do in constant time, except for maybe logarithmic and variable names for the lookup and addition here. And therefore, the amount of work that's returned by this is going to be within a constant factor of the RAM simulation. So what I'm saying is this is an reasonably accurate model. Now, it turns out we can extend this to the parallel case, and we'll talk more, but the parallel case is more interesting. It involves scheduling. But all I'm going to say now is that instead of, we have a variant of the CEK machine, a parallel CEK, and when we evaluate E1 and E2, what we have is instead of a single control state there, triple, we have a sequence of triples. And we can evaluate all that sequence in parallel, or any subset of them. Okay, and the job of deciding which subset to do is called the scheduler, and we can schedule those. And the point is, if one of them looked like this, E1, E2 goes to this, instead of writing it like we did before, we want to say it runs in parallel. So we're going to fork off two processes. So we take this one process that's evaluating E1, E2 with environment E and continuation K, and we fork off two processes, one which is evaluating E1, and the other which is evaluating E2. And now they can go in parallel. And I can write down a machine like this, and then I can simulate it, and I can eventually simulate it on a PRAM and get simulation results. And to sum up, these are actually the simulation results you get. What happened to the, I think I dropped the, this assumes, yeah, so this is assuming the number of constants is, I think I dropped the previous slides. This assumes the number of variables is constant. If it wasn't, then I have to multiply that W by this log number of variables term. And that's just for the lookup in the environments. Okay, but if I write my lambda expressions with a constant number of variables, then this is the bound. And so,
constant by definition, guy? Is it program size is constant, right?
No, because remember, I'm in this model now, before we introduce arrays, the only way I have to represent data is by lambda expressions themselves. So if I had a list, my input was, let's say I'm doing sorting, and I'm sorting a list of size n. What would it look like in this model? We'd have some expression E1, which is my sort routine. And then I had my data, and the only way I can represent data is using lambda expressions, because that's the only thing I have so far, is lambda expressions, would be another E2, and this would actually be a representation of my data. And we showed how to encode pairs, and we can nest the pairs so we can make a list, or we can make a tree, we can encode all those things in E2. This, you're correct. This one's obviously going to have a constant number of variables. This one, you could think of some crazy scheme of encoding this which had non-constant. All standard schemes, like if I encode it using my rules of pairs, would only have a constant over on this side. Because this is not constant size. This is my input. This is my list. This is my thing that's of size n. This is my code. And this is fixed length. Is that clear? That's actually a good point you made. Yeah, because you have to ask yourself, what is n in this case?
So it's not a fundamental thing you're saying. The signature encoding, we can eliminate this times.
By using what?
By using a fancier encoding of the input, we can eliminate this.
Yes, yeah, that's correct. That's why I'm sort of assuming it's, that's why I left it off of this slide here. But it's a technicality that you just have to be a little thing, because you can sort of cheat and create. You can actually encode permutations using a linear number of variables that allow you to cheat in various ways, but we'll ignore it. The important thing here, and we'll talk more about this next time, is if you look at the simulation result, we're dividing the work by the number of processes. So this is saying how long does it take to simulate this on a machine with p processes. And this is why the work matters. Someone asked earlier why the work matters. We're dividing the work by the number of processes. We want that to be the dominant term, right? Ideally, that's if we wanted linear speed up. Ideally, we want linear speed ups. I'm doing some work sorting on one processor. If I have 100 processors, ideally, I'd like it to run 100 times faster, right? Because I paid for 100 processors, I'd like it to run 100 times faster. That first term is that. It's saying we're going to divide it by the number of processors. You got some number of work. I divide it by the number of processors. Now it's 100 times faster. I got 100 processors. Okay, but you got this little nasty term afterwards. So that's not always possible because maybe your program's inherently sequential, and that would show up in that second term. Because then the D, if your program was completely sequential, your D would be basically W itself. And this would become much more, you wouldn't gain anything with X processes. So the first term sort of says that's sort of the ideal speed up. And what this says is I can simulate this lambda calculus in the cost model I gave. It's going to give me some W back. I divide that by the number of processes. It's going to give me some D back. And I add that on plus this log p time. It turns out that you can actually get rid of log p, and I believe what Umut's going to describe today, you can actually do this in W of p plus d plus log p instead of the multiplying. So that you basically, it's d plus, so it's an improved result. The one I have here is what was originally proved, and then that was proved later. I should point out that you can't possibly do better than W over p the max of these two, because we can't do better than linear speed up. If you've got p processes, we can't speed it up by more than a factor of p, right? And we can't do better than d, because d is a critical path length. So it's a sequence of dependence. And if you notice that if let's ignore the log p there, which, as I mentioned, maybe we can get rid of anyway, then these two are within a constant factor of each other, the sum of those two terms and the max of them. So it's about as good as we can hope to get. So what it says is we can evaluate algorithms, the complexity of algorithms in this cost model, and then map it to something that maybe looks more realistic. Now, once you believe this cost model is valid, then you can just stick to it and not worry about this. But you might want to know on some number of processes and get approximately sense of how fast it will run. You can plug this equation in. By the way, we refer to the ratio of W and P to the parallelism. That's an important idea, which is if you look at W over P, this is called the parallelism. And it roughly indicates the number of, W over D, over the span. It roughly indicates the number of processes you can make use of in your program effectively. It is the point, again, if you ignore the log p, which is actually going to be pretty small because nowadays p is only, we got a few dozen of them or something, then that's the point where these two terms are equal, right? Because if W over D equals P, then W over P plus D equal each other. And so that's a point where if you have fewer processes, the first term will dominate, and you'll be happy. And if you have more, you're basically not going to get much improvement. Because if you add more and more processes, at most you can get a factor of 2 improvement by completely getting rid of that first term. So this point is approximately the number of processes you can effectively make use of. It's called a parallelism. So if you analyze an algorithm, you figure that out. And that'll tell you how much parallelism it is. Okay, there's one more thing. As I mentioned before, you can add constants to this. And in particular, from now on, I'm going to assuming that the integers, I'm going to build in integers, add them to my Lambda calculus. And they're going to be unit costs to add them. Okay, and I'm going to bound the size of these integers to be basically the size of my input, so that I can't cheat in the same way as I talked about in the RAM, where I have infinite unbounded number of bits. But then I assume that I can basically add 2 numbers in constant time. So I just add these constants to the Lambda calculus. The integers 0 to n, addition. These are curried version of plus, the curried versions of less than, etc. Okay, then let me finish off by quickly analyzing some algorithm. I say, let's say I have quicksort. I claim this is just Lambda calculus. There's nothing in here that I haven't described already. Right? I've described how to simulate let. I've described how to simulate if then else. Okay. I have to show code for some of the functions like filter and append. I described how to simulate a linked list. I'm assuming this is working a linked list using pairs. This is just the Lambda calculus with some few extensions. There's nothing here. I can analyze it. Okay, that's what's the beauty of the Lambda calculus. It's a Lambda calculus to read real code is 5 minutes. Okay, so well, that's okay. Here's a version using lists. Okay, and like I said, I can encode linked lists using the pairs I described earlier. I can easily encode filter and append. Okay, I'm not going to actually show the code here using standard, recursive routines.
So for the previous implementation, you showed a random pivot. Is that randelt?
Randelt, yeah.
How do you get a random out of the?
I'm cheating here. It can't. I'm assuming this is purely deterministic. So this is what I'm actually doing now is I'm taking the first element, okay, and so the way I could analyze this is I could say what's the expected time over all input orderings. So if I had a randomly permuted input, this would give me n log n time. So you could then analyze this algorithm in this model. And what would you get? You'd get a work that's n log n. Again, this would be expected case, assuming all random inputs. And you could ask, well, what's the span? The span's going to be linear. So it's not very, it's almost going to be as high as the work. And the reason is, well, the partitions on the linked list is going to take me linear, there's a dependence there. It's going to take me linear depth to partition. It's going to take me linear depth to append, because I have to take this list and I have to append another list on the front. And I basically, if you probably know how append would work in a linked list, right? I do them one by one. So this gives me a parallelism with log n, which means I can make use of log n processes. It's not a particularly interesting parallelism. It's not very parallel. Okay. Can someone tell me how I might be able to get much more parallelism out of quicksort? What? Can I get more parallelism? So the reason I'm getting parallelism out of quicksort in this case here is I should point out that I can apply in my Lambda calculus, the 2 quicksorts here can be applied in parallel. Because just by then I don't have to and any notations. This is implicit parallelism here. I'm just saying whenever you have 2 lambdas next to each other, but 2 things, I can apply them. So I'm going to apply those 2 things in parallel. And then I get this sort of dependence tag here where I basically, first partition, I make 2 recursive calls. They happen in parallel. They each make, so someone asked before what happens if I nest it. They each make recursive calls. They happen in parallel. You know, I only showed it a few levels, but it keeps going until the leaves of the recursion, and then it pops up. And so if you want to know what the total work is, well, it's the same as the cost of the sequential algorithm. I don't even have to reanalyze it. I just said I already did it sequentially. The span is going to be this n, and then each of these are about half as long. Now, to show this technically, because of the randomization, is a little trickier, but you'll have to believe me on that. And then I do, 4 things. And so the total is going to be basically n plus n over 2 plus n over 4, et cetera, and then summed up. And so that's a geometric increasing sum. So the overall depth is n. So I do get some parallelism from the recursive calls to quicksort. But is there a way I can get more parallelism?
Increase more children so that span would be more.
Yeah, that would actually change. I want to do it without even changing the algorithm. Maybe the data representation. The filter, yeah. The point is, I'm saying do it on a linked list. So instead of doing it on a linked list, do it on a tree. Let's say that my sequence, input sequence, is represented in a balanced tree of depth log n. Right? Now what can happen is I can do the filter in parallel, because I could now recursively filter the left and the right in parallel. And then it would recurse, right? So here's my append and filter written on a tree. That's the whole code. And it's pretty much just the Lambda Calculus with some sugar added, right? Using the extensions I mentioned. So we have this tree, and we have a left and a right branch. And for the filter, we basically filter the left. We filter the right. And then we append them together. So this filter and filter. And append here is unit time, because it's just creating a new node at the root. So I could rate it like this. And now you can have that, just changing my representation of my input sequences. I change it to a tree. And now I can ask you, well, what's the complexity of this algorithm? Can someone guess what the work? The work stays the same, because the work is actually, here's efficient. The filter does linear work. The append is actually constant work now, but so it'll be dominated. What did someone say? Log n. That's, yeah, pretty close. Well, it turns out that the filter itself is going to take log n, because it goes down the tree, right? And the tree is balanced. But remember that I've got a filter, if you look at it recursively, I've got a filter at the root, and it makes, and that's going to do my split at my partition at the root. And then I have to partition everything that's less and everything's greater. And there's going to be another filter here and another filter here. And then each of those are going to make recursive calls, and there's going to be another filter here. So what's the overall depth going to be? What? The depth, the span, sorry. Span. The work is going to stay the same as n log n and expected. And let's assume that it divides perfectly half and half, so we don't have to worry about the randomization. What's going to be log squared? Because it's going to be log at each level, and there's going to be log n levels of recursion. Okay. So now we have an algorithm where this pictorially shows it. This is supposed to show sort of the dependent structure. So each of those blocks is basically a filter. So each of those blocks is itself log n to do the filter, because it works recursively on the tree. And then we split it in half, and so there's log n levels. So it's a product of the two. So you get this log squared, and so that ends up being the span. And again, this is all expected case, and you have to analyze it over randomized. And doing the full analysis is a bit messy, just like even the sequential analysis of expected case. And so now we've got a lot of parallelism. Now we've got a very parallel algorithm. We got one that runs in basically the amount of processes we can use are n over. If we're sorting, a billion keys, we've got a billion. We can make use of a billion over 30 million processes. It's hard to find a machine with, 60 processes, yet 30 million. But the nice thing about this model is we don't have to. We could run this on one processor and it would be equally good as quicksort, or we can run it in two processors. What the bound I showed basically says is as long as you run it in less than 30 million processors, or something on that order, you're in good shape. And we get an efficient algorithm. So the combination of the work and the depth is what tells you about how many processes we can make use of. And like I said, we want the work to be efficient because ideally we want to get linear speed up over the sequential algorithm. And if we had that W over P term. So if W equals the sequential time, we divide it by P, we'll get this linear speed up. Okay, so that's really all I was going to say. I just wanted to remind you about one sort of key point about analyzing algorithms, because this will come up over and over again in the examples we give, is that when you combine two things, two pieces of code, if they happen sequentially, if one happens after the other, then what we're going to do is we're going to add both the work and the span. Because for the work, well, we have to do all the work. And for the span, we have to finish the first one before we do the other one, so the critical path is the sum of them. On the other hand, if we're doing two things in parallel, if we have E1 and E2, and we're evaluating them in parallel, or the two instances of quicksort, and we're evaluating in parallel, then we add the work, and we take the max of the span. Because if you look at, that was what the rules were. Remember, we wrote that when we wrote down the rules, we said it was the max of the span. So that's what we should remember, is this basically, programming is composition. Well, at least functional programming is. I guess non-functional programming is non-compositional, but functional programming is purely compositional. And so when there's basically two ways to compose here, sequential composition and parallel. And if we do it sequentially, both the work and the span add. Otherwise, for the parallel case, the work adds and the span has a max. And this then allows us to write recurrences for the things like divide and conquer, because let's say we had a divide and conquer algorithm which divides exactly in half, then the work would be the sum of the two recursive calls plus the time to split plus the time to join, and the span would be we don't have to multiply it by 2 here, because assuming if they're both the same, right, we drop the 2 here, right, because it's the max. The max of A and A is A. So since we're assuming that the S of some integer is a fixed, they're both going to be the same. So it's a max of S of n over 2 and S of n over 2, which is just S of n over 2. And then, of course, we're going to look at the span of split and the span of join. Okay. And so that's going to come up over and over again. Okay, so that's it. I just want to say that we'll be talking about adding, we'll get into this tomorrow, we'll add in some primitive arrays, and so I'm not going to discuss that now, and we'll add some built-in things. So the conclusion is there's 2 parts to a cost mode. I guess it means model there, typo, sorry. One is the model itself, and the other is simulation results. And the reason the simulation results are important is because otherwise you could define an arbitrary model that has no meaning. And in our case, we defined this model based on Lambda Calculus, showed how the Lambda Calculus is inherently parallel, and the simulation results showed us that we can then map it onto machine models which other people accept as reasonable machine models. The PRAM, the parallel random access machine, is what's used by most of the parallel algorithms community for analyzing algorithms. And then I just argued that the Lambda Calculus is great, and I'm not biased here at all, but since you're all people interested in PL, you probably all feel the same way. So, okay, so that's it. Any other questions? Yeah?
So, when we talk about getting the speed up using multiple cores, there are issues like, because of the data movement, like cache coherence and locality of data. So are we going to talk about that?
We're not going to talk about at the level of cache coherence, because that's done in the hardware. We are going to, in the next talk about the actual scheduling. So how do you we have all these different tasks, how do you map them to the processes? So how do you take them to the processes? And so we will talk about it at that level. With the cache coherence. We're also not going to talk about cache effects. I should point out most of the theory work on algorithm also doesn't talk about cache effects. RAM has no notion of cache effects. I did mention at the beginning a paper that Bob Harper and I worked, that was in Popple a couple years ago, where we did look at cache effects. But that's beyond the scope of these presentations. Any other questions? Okay. Oh, one more, Jesse. Oh, I didn't explain, well, as I probably should have dropped it because Umut's going to show a version that doesn't have a log p term. It has to do with, there's a cost to load balancing. It's exactly the scheduling problem. You have all these jobs to do, and you have to assign them to the processes. And that log p term in the version I showed comes from that assignment. Okay, but it turns out that more advanced techniques allow you to do it without that log p term. So we can get rid of it. Or it's an additive term instead of sum. But it comes from the load balancing issues. Okay, thank you.